let's start off today by doing a couple of review items from what we saw on Monday related to just types of intermolecular forces. So our first question for today is this. I've got four substances here: xenon, methylamine, an aqueous solution of potassium carbonate, and hydrogen iodide. What kinds of forces are predominant in each of those substances? So just as an aid here, we're going to draw out the structure of the methylamine. Just so that you have an idea of kind of how it's put together. All right, somebody give me a pair that they know for sure. Okay, xenon and London dispersion forces. That is a correct matchup. Now, how do we know that that's a correct matchup? Well, all of these other forces rely on polar molecules. To be a molecule, you have to have more than one element. So when it comes to atomic substances, they can't form dipoles on their own. They can only form dipoles when they bond. So xenon, the only forces that could possibly exist in xenon are those dispersion forces, the ones that come from the random movement of electrons. Okay, so that's a good first pair. Any other, Eden? Yeah. So hydrogen bonding for the methylamine. That's also a good match. How do we know that? Well, remember the two conditions for hydrogen bonding. I have to have something that is polar, asymmetrical. That certainly qualifies. And I have to have something that has one of those special kinds of bonds, NH-OH-FH. Well, the amine part of methylamine has two nitrogen to hydrogen bonds. That's one of the requirements. So I've got polar and I've got NH. I've got both. I've got hydrogen bonding here. Okay, so we've made two of the determinations. What about the potassium carbonate? Yeah, it's an ion dipole. Remember what we need for ion dipole. We need an ion and we need something polar to make the dipoles. Well, the ions come from the potassium carbonate, the potassium ion and the carbonate ion. The dipole comes from water. The fact that it's aqueous means that it's dissolved in water. So I've got ions from the potassium and the carbonate. I've got dipoles from the water molecules. When those two things interact, ion dipole forces are the result. And then the last one, HI to dipole. Well, process of elimination takes us there. We also know hydrogen iodide, that's a polar bond, right? We know that there is an unevenness of sharing there because hydrogen and iodine have different electronegativities. And so any unevenness of sharing, any asymmetry here is going to result in a polar molecule, or at least a polar bond. Since this is the only bond in the molecule, it's also a polar molecule. So that's the correct lineup. Xenon to London dispersion forces, methylamine to hydrogen bonding, potassium carbonate solution to ion dipole, and hydrogen iodide to the dipole-dipole forces. All right, let's answer one other question out of this. We just talked about the methylamine here. What intermolecular forces are present in this methylamine? Well, we already know from the last slide, we already matched it up with hydrogen bonding, so we know it has hydrogen bonding there. The question is hydrogen bonding the only force present inside of the methylamine? And the question is, or the answer there rather, is no. Let me ask you this question. Does methylamine contain electrons? Yeah, it's as obvious as it seems. If it contains electrons, by default, it contains London dispersion forces. London dispersion forces are present in all substances that have electrons because those electrons move and create temporary dipoles. So London dispersion forces are an automatic yes, regardless of the substance. Doesn't matter if it's polar or non-polar, London dispersion forces are always going to be there. So we don't have any ions, so we can eliminate ion dipole forces. We know that in addition to the hydrogen bonding, at the very least, we have London dispersion forces. The question is, do we have dipole-dipole forces as well? Remember the conditions for hydrogen bonding. In addition to having those special bonds, what is the first condition of hydrogen bonding? I have to have something that's polar. By virtue of it being polar, I'm going to have dipole-dipole forces. So all three of these forces are going to be present in this molecule. So letter B is our correct answer here. The thing to remember is that these intermolecular forces are additive. One doesn't replace the other. They add on to each other. They supplement each other. And so from that perspective, we look at something like this and say, oh, it's got three intermolecular forces working at it. It must have considerably more intermolecular force, more strength in those forces than similar size molecules that might only have one or two of those forces. The forces are summative, cumulative. Okay. Now we get into kind of where all of this stuff applies. So we're going to talk a lot today about liquid properties. And the reason we're going to talk about liquid properties is that even though intermolecular forces exist in the solid phase, most physical properties associated with the solid phase aren't nearly as affected by the strength of intermolecular forces as other things. Intermolecular forces have a much more significant impact on the liquid phase than they do on the solid phase. And one of the main reasons for that is this idea here. The kinetic energy of the liquids and the intermolecular forces that exist between the liquids are roughly comparable in their magnitude. What that means, that energy of motion in those liquid molecules is roughly close to the energy of attraction between the molecules and each other. And so when we have higher degrees of intermolecular force, that's going to have a much more significant impact on the liquid phase because there is so much more comparable in size to energy. The other thing that we would want to look at is this idea. We know that the attractions decrease with distance. And so the more energy that is put into that liquid system, the more that those molecules can be separated from each other because of that faster motion, the less those attractive forces are going to weigh into them. So when we start to evaluate the strength of intermolecular forces, what we need to look at primarily is the strength of the forces impact the properties the greatest. Stronger intermolecular forces have stronger impacts on certain kinds of physical properties. And we're going to start looking at some of those physical properties that get impacted as a result. The first one we're going to look at is viscosity. Viscosity is defined as the resistance to flow for a particular liquid. Viscosity and kinetic energy do have kind of an inverse relationship to each other. There is a temperature dependence portion on viscosity. Now, the book here is giving maple syrup as an example. If you've ever made pancakes or waffles at home, pulled the bottle of maple syrup or imitation maple syrup out of the refrigerator, you'll notice that it can be kind of hard to get that stuff out of there, especially if there isn't a whole lot of syrup left in the bottle. It kind of sticks to itself. It sticks to the sides of the bottle. Well, the main reason for that is the intermolecular forces that exist inside of that syrup cause the molecules to stay stuck together. And if you're pulling it directly out of your refrigerator, which might be at somewhere like 37, 38 degrees Fahrenheit, the lack of kinetic energy in those molecules, because it's so darn cold in the refrigerator, is going to make that viscosity even greater. But you can pretty simply fix it as well. Take that bottle of syrup, put it in the microwave for a few seconds. The energy of the microwaves will warm up the syrup, and suddenly the viscosity is going to be a lot easier. Or you put it in a pan of hot water and do kind of the same thing. Increase the kinetic energy of the molecules, and suddenly it loosens up the syrup a lot. You can pour it out pretty easily. Now, why does maple syrup have this kind of viscosity? Well, if we get down to the structural components of syrup, what we find in there is that syrup is basically sugar and water in a highly concentrated solution. Well, if I look at the structures of these sugar molecules, what do I see a whole bunch of? I see a whole bunch of OHs. Can't tell from this picture, but the sugar molecules actually don't exist in these chain-like structures. They exist in ring-like structures. And in those ring-like structures, what do those OH groups do? They stand up. I've got polar centers that are very highly hydrobonding friendly because I've got all these potential hydrogen bonds there. So in a molecule of glucose, I see 5 potential hydrogen bonds. The molecule of fructose, I see 4, maybe 5 potential hydrogen bonds. That's significant. Take those hydrogen bonds, combine them with the 2 hydrogen bonds that you get off of each water molecule, and you've got a network of hydrogen bonding that can be really tough to separate. And if the concentration is so great that those molecules are all on top of each other, that's how we get the viscosity that we're talking about here. And you can imagine, if, especially with the cold aspect of it, that can really impact the ability of that substance to move around and flow. Now, viscosity is not limited to just hydrogen bonding and polar molecules. In nonpolar molecules, so motor oil, for example, you can see different kinds of viscosities taking hold there. So, for example, we have different types of hydrocarbons that can be used in the creation of motor oil to give different viscosities. As we talked about on Monday, these long branch molecules tend to interact very well with each other in terms of London dispersion forces. They have great surface area. So these kinds of things have a higher viscosity as a result of those increased hydrogen bonds. And so we find them being used for a summertime kinds of applications where we want the higher viscosity because the temperature is going to naturally loosen up the molecules in general. These branch molecules here, which we know have lower intermolecular forces because they can't get as close to each other because of all of the branching there. Where do we use them? We use them more in winter kinds of applications, where the decrease of intermolecular force also leads to a decrease in viscosity, so that in the cold winter months, the oil doesn't freeze up. It doesn't lock down and make the engine unusable. So you can see in different kinds of motor oils, different combinations of these things being present. And if you get into some of those blended oils, 10W30, 15W40, well, what you get is a mixture of these kinds of hydrocarbons. The W there stands for winter, and it gives you a viscosity rating for colder months. So part of the blend has some of this stuff in it to stand up to colder temperatures. Part of the blend has some of the higher chain stuff in it to stand up to higher temperatures. And both are actually present in the same oil at the same time. We can also talk about surface tension. Surface tension is a phenomenon that exists in certain types of molecules, especially water we see this with, where the intermolecular forces inside of the substance basically cause it to bead up near the surface. And what we get is an interesting kind of interplay between the intermolecular forces that are holding the substance together and the gravitational forces that are trying to break through. And so if you have objects that are either really low in density, so aluminum coins kind of fit that bill. Aluminum is a relatively low density metal. I think it's density somewhere around 2.7 relative to the 1.0 for water. Well, if you spread that out, the surface tension, the forces of those intermolecular forces, those hydrogen bonds pushing up on that aluminum coin, actually are greater than the gravitational forces that are pushing that aluminum coin down. It floats on the top. Insects like water striders kind of work on the same principle. They have leveraged their ability to put pressure on the water to the point where the surface tension of the water actually pushes up greater than the gravitational force pushes down on that insect. So as a result, they're able to kind of skim across the surface of the water as opposed to having this slog through it. Okay, next big idea, vapor pressure and evaporation. Now, these two concepts, vapor pressure and evaporation, are very similar to each other. Really, the only difference between vapor pressure and evaporation is whether we are dealing with an open container or a closed container. In an open container, we call it evaporation. Basically, what happens is that the kinetic energy of the molecules itself becomes large enough that some of those molecules are able to break free from the intermolecular forces and vaporize, go up into the gas phase. This is a phenomenon that we've seen many, many times in our lives. You have a cup of water, you put it on the shelf, you forget about it, go and do something else, you come back, the water level inside of the cup has gone down because the water has evaporated. Happens a lot. Why does it happen? Again, it comes down to kinetic energy versus intermolecular force. And in this case, kinetic energy has won out for that particular molecule, and it has escaped the liquid phase. Vapor pressure is basically the same phenomenon. Kinetic energy of the liquid allows certain molecules to escape to the vapor phase. The only difference is that this is in a closed system instead of an open system. And in this closed system, instead of the evaporated molecules just kind of floating away, they're trapped. And being trapped, they're going to be able to exert a pressure on their outside container. And we can actually measure what that pressure is. So you think back to the lab that you just did. You had to take into consideration the vapor pressure of water. How did we know what the vapor pressure of water was at those given temperatures? At some point in time, we had to measure it. And so using a pressure sensor or a barometer or some other kind of instrument, we could set water at these different temperatures and measure how much pressure they would exert on the container when they did so. Because this is a closed system, we also see what is called equilibrium taking place, where eventually there will be an interplay between the gas and the liquid phases. And they'll coexist once we hit that vapor pressure. And so some of the gas molecules will turn into liquids, some of the liquid molecules will turn into gas, but they'll constantly be interchanging at that vapor pressure. Now, here's where the relationship to intermolecular forces come in. If we have a high amount of intermolecular force, so we look at the molecule, we see, okay, it's got a lot of intermolecular forces. Its liquid phase is going to be pretty pronounced, pretty strong. What that means is that if the liquid molecules are attracted to each other, they're far less likely to evaporate. So the stronger the forces are in the liquid phase, the much less likely evaporation will be. And since if evaporation is less likely, that means we're going to see a lower vapor pressure. The other thing that we also have to consider is that there is a relationship between temperature and vapor pressure. And this should be kind of intuitive to us. We know that when we increase the temperature, we're increasing the kinetic energy. So if those molecules are moving faster and with more energy, the likelihood of one of those molecules escaping the liquid phase and going into the vapor becomes that much more likely. So there is a definite relationship between temperature and vapor pressure. As the temperature increases, so does the vapor pressure. To a particular end. And that particular end we call boiling. So thus far, when we've talked about boiling and boiling point, we have been referring to what is called the normal boiling point. So when we say that water boils at 100 degrees Celsius, we've been referring to the normal boiling point. That is the boiling point that is measured at normal atmospheric conditions, 1.00 atmospheres. The atmospheric pressure at sea level. What we have to consider is that boiling can occur at other conditions other than the normal condition. So we need a definition that helps us to define when boiling actually takes place. And the answer to that is a relationship of pressure. In particular, the vapor pressure of the liquid relative to the external pressure above the liquid. So by definition, boiling is something that takes place when the vapor pressure of a liquid matches the atmospheric pressure above the liquid. And so at normal conditions, we get the normal boiling point. But what if we aren't at normal conditions? What if we are on the top of a mountain where the air is thinner and the vapor and the pressure is less? Well, what does that mean? Well, if the atmospheric pressure comes down, that means that the vapor pressure isn't going to have to go as high to match atmospheric. The water is going to boil at a lower temperature. Which is why if you've ever read certain types of recipes, they give you high altitude directions. So if you're cooking this recipe in the middle of the Sierra Nevada mountains or in Denver, Colorado, it's going to require slightly different directions. Why is that the case? Well, because at that higher elevation, the boiling point is not going to be nearly as high of a temperature. And so if water boils at 91 degrees where you live, it's going to take more than 5 minutes to cook your spaghetti because it's now being cooked at 91 degrees instead of 100 degrees. So you have to take those kinds of things into consideration. So speaking of, here are several situations where we can see water boil. Under which of these conditions would the boiling point actually be above 100 degrees Celsius? So give that a thought here. if we're trying to boil water at greater than 100 degrees Celsius, what kind of atmospheric pressure are we looking for? Are we looking for above normal or below normal? We need to be above. Because again, if vapor pressure and atmospheric pressure meet at the boiling point, we're going to need higher pressures to get that temperature up above 100 degrees. So most of these scenarios involve lower than atmospheric pressure. So if I'm in an evacuated chamber, that's going to be low. You're going to see a lower boiling point as a result. On top of the mountain, lower pressure. Eye of a hurricane, lower pressure. At sea level, that's actually just normal. So we would expect it to boil right at 100 degrees on Daytona Beach. The submarine, what we have to consider is that a submarine, by going to the lower depths of the ocean, is going to be experiencing a lot of external pressure. The only way to keep your submarine from not being crushed by the weight of the water on top of it is that you have to pressurize it. So just like the cabin of an airplane is pressurized to prevent similar kinds of forces from acting upon it, same kind of thing here. Pressurization happens to keep the submarine intact, which means that the atmospheric pressure inside of that submarine is going to be greater than 1 atmosphere. And so it's going to require more energy to boil it. Our boiling point would be above 100 degrees in that circumstance. All right, I'm going to skip over this business with phase changes. We've talked a lot about phase changes already. All that we really can provide now is context, because we know that when phase changes occur, they are now coming at the cost of intermolecular forces if we're adding energy to them, or we are adding intermolecular forces in those exothermic processes that are ditching energy along the way. We want to end here talking about phase diagrams. Phase diagrams are basically graphs. What these graphs do is they help to illustrate the relationship between temperature and pressure. So going back to what we were just talking about with regard to, how a boiling point can change based upon atmospheric conditions. What a phase diagram would do would actually be to plot that to help us predict when those kinds of transitions take place. So in a phase diagram, what we ultimately will see is that there are kind of set regions of a phase diagram. Over here, where we tend to see high pressure and low temperature, we tend to see solid phase kinds of materials. Over here, where we tend to see kind of low pressure but high temperature, we tend to see things in the gas phase. Here in the middle, we tend to have the liquid phase. But what this graph tells us is it allows us to say, okay, if I have this substance at this temperature and that pressure, what should I expect to be seeing inside of my flask? And I can look at the graph and say, oh, okay, well, at that temperature and that pressure, you should expect to see a solid, or you should expect to see a gas. Now, a couple of other key areas that we want to look at in particular are these critical points. So the first of these critical points is something called the triple point. The triple point can exist in any phase diagram where we have 3 phases present at the same time. So in this particular phase diagram, we see that the solid, the liquid, and the gas are all present at the same time at that particular temperature and pressure condition. It's a very odd phenomenon. A critical point, on the other hand, is a temperature and pressure condition where that is the last temperature and pressure condition where we actually can tell the difference between between liquid and gas. At temperatures and pressures above the critical point, our substance moves into a phase known as a supercritical fluid. Now, supercritical fluids have some interesting kinds of implications on them as well, which we won't talk about, but if you look into certain things like, one of the ways that you can decaffeinate coffee. So if you want to make decaf coffee, commercially, one way to do it is you can extract it using some organic chemicals, which works, but you kind of start going into the ick factor on, are there any residues being left behind by those organics? Another way is through supercritical fluids. Certain kinds of supercritical fluids will actually dissolve the caffeine and leave everything else pretty much behind. And so caffeine gets removed, you still have the coffee bean and all of its chemical agents pretty much intact, which allows the coffee to still kind of taste like coffee, even though it doesn't have caffeine in it. So that's, there are some really cool practical applications to supercritical fluids, which again, I wish we had more time to talk about because it's where this kind of stuff actually gets super interesting. But we've got 3 minutes left. Let's get into the stuff that actually kind of matters the most to you. What are the kinds of things that you can be asked about this? What kinds of things might you be asked to say or do? So here's an example. Here I have the phase diagram of carbon dioxide. And so in this phase diagram, again, I can see I've got the solid region here where we have high pressures. I have the gas region over here where we have high temperatures. I've got the liquid region kind of in between. And here after the critical point, I see that we have supercritical fluid. And you can see off of this, one of the reasons why carbon dioxide is used in the supercritical phase is that temperature that we need for it is about 30 degrees Celsius. So it doesn't require a whole lot of temperature. It does require a good bit of pressure. But even at that, 100 atmospheres of pressure isn't as much as you think it is. A lot of compressed air tanks can hold that kind of pressure. So it's really not as bad as you think. So, question, what is the expected phase of matter at 10 atmospheres and negative 80 Celsius? Well, easiest way to go about doing that is to literally just kind of draw it out. So at 10 atmospheres, that's right here. I'm going to draw best approximation I can of a straight line. Negative 80, same kind of thing. And I can see, okay, the crosshairs of that is firmly in the solid region. So what is the expected phase of matter? Well, I'd expect the solid based upon those lines that I just drew. Okay, what's a set of conditions where we would see carbon dioxide melting or freezing? Well, again, I can go back to, just drawing some lines out here. Let's go to 100 atmospheres. Where does that 100 atmospheres cross this blue line between the liquid and the solid? Well, somewhere right around there, I'd say. And so, we don't have a very good scale here, so we're going to have to just kind of do our best. But at 100 atmospheres, and let's say about negative 59 degrees Celsius, we would see melting or freezing or both, if they're in equilibrium with each other, happening at those conditions. Why don't we see liquid carbon dioxide when we use dry ice? Well, Same kind of question here. We do most of our work here at atmospheric pressure. So let's look at that tie line there. 1 atmosphere, I can see that we have a solid to gas transition over here at the sublimation point. I don't see any kind of transition into the liquid phase. So why does that happen? Why don't we see it? At 1 atmosphere of pressure, carbon dioxide does not exist as a liquid. So as you're going through your homework problems, and I'd encourage you to go ahead and just kind of put those on the back burner, unless you just have time this afternoon to kind of do it quickly. You should be spending most of your time over the next couple of days getting ready for the exam on Friday. But these are the kinds of questions that you'd be asked regarding phase diagrams. And so if you can handle those, you're going to be in really good shape for the quiz on Monday. Because most of the stuff on that quiz Monday is going to be these kinds of questions. You know, can you interpret a phase diagram? Can you differentiate between the different kinds of intermolecular forces? If I give you a couple of substances, can you tell me which one's going to have the greater boiling point or the lesser boiling point based upon their structure? So can you identify polar versus non-polar? Can you identify hydrogen bonding when it exists? Those are the kinds of things you're going to be asked in that quiz. So, and that's the kind of stuff that's in this assignment 9-2 and in the review as well. If you get caught up on anything, feel free to reach out to me about it. But get ready for that exam on Friday. That should be your primary focus now. I'll see you then.